Hello, this is Ian Woolf, and here's another blast from the past. It's a Diffusion science radio show, first recorded in October 2008.
Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology,
astroseismology,
magnetism, the dark side,
genetically engineered potatoes,
Planetoid.
planetoid.
I love that word.
Hello and welcome to Diffusion. Relax while we lovingly drizzle weird and wonderful science into your brain. I'm Ian Woolf. On this edition, we'll feature quantum teleportation and the science of radio. But first up, here's the news. Medical chocolate is the new product from Mars. The flavanol compounds in cocoa have previously been found to help vascular blood flow for a healthy heart. New research from Harvard University and the Mars Corporation has been published in the Neuropsychiatric Disease and Treatment Journal. The researchers suggest that drinking chocolate made with high levels of flavanols will bring long-term improvements in blood flow to the brain. An improved flow of blood to the brain will help people recover from conditions such as dementia and stroke. The study looked at adults aged between 59 and 83 who regularly drank a chocolate drink rich in cocoa flavanols made using the patented Mars Cocoa Pro process. The people all had an 8% increase in blood flow to the brain after only a week, and a 10% increase after 2 weeks. The researchers from Mars and Harvard both found short and long-term benefits from the flavanol-rich chocolate drink. When the flow of blood to the brain slows over time, the result can be structural damage and dementia. Increasing the blood flow may slow or even stop this decline. So drink and eat more chocolate and expect a flood of new medical chocolate products on the market, each promising to improve the circulation of blood to your brain, as well as fat to your hips and cash from your wallet. When a woman says hello, she might also be telling you how fertile she is. Researchers suggest that a woman raises the pitch of her voice during her most fertile period of the month as an unconscious signal that she's ready. Greg Bryant and Marty Hasselson of the Center for Behavior, Evolution and Culture at the University of California in Los Angeles asked 69 women to record their voice when they're at high and low fertility points in their menstrual cycle. An analysis of the recordings revealed the closer a woman was to ovulation, the higher the pitch of her voice. The increase in tone was only slight. It wasn't Minnie Mouse on helium, but the peaks were enough to be picked up by the voice decoder, and presumably by the male ear as well. The difference was the greatest on the 2 days preceding ovulation, when fertility within the cycle is the highest. This distinction only occurred when the volunteer, amongst the sentences she was asked to speak, introduced herself. So she's only giving her fertility away when she says hello. The scientists suggest the pitch change happens because men are lured by a more feminine voice in a woman, and women respond to the instinct. Sexual signals and reproductive fitness are strongly associated with voice, which is why women are often drawn to men with the husky voice of the supposed alpha male. Previous research has found changes to body scent, an increase in flirtation, a shift towards more fashionable dress styles, and a preference for more masculine men when women are in mid-cycle and fertile. Last year, investigators found that lap dancers earned more tips when they were fertile. On the other hand, a vocal shift towards hoarseness has been found at the time of menstruation. The researchers say these results call into question the traditional assumption that humans differ from other primates in the lack of any obvious cues of fertility. It gives the phrase, "You had me at hello," a whole new meaning. I spoke with Dr. Samuel Braunstein about quantum teleportation.
Well, in its simplest sense, quantum teleportation is taking some physical system and being able to move it from one place to another without it actually moving in the intervening space. And so it's like a disembodied transport. Actually, a little bit like what you see on Star Trek. Say Captain Kirk is in Starship Enterprise, and then he disappears, and then he reappears on some planet. In quantum teleportation, we take some physical system, say a single photon or a beam of light, much smaller than Captain Kirk, and then we perform measurements on it, which destroys it, so in a sense it disappears, and then from the information we have available there, we send that information down a classical communication channel to a receiver where the state is reconstructed. Now that classical communication, that classical information is not enough to reproduce the original state. The reason for that is because of no cloning.
So does this mean that in the old classical Star Trek system you destroy the original, so he dies, and then you make a copy that's not quite perfect at the other end?
Well, in principle, in quantum teleportation, you could make an exact replica. There'd always be some limitations due to imperfect technology. Now, what quantum mechanics tells you is we have a description of systems in terms of a wave function. And it's not that the wave function is really reality, but that's the description that quantum mechanics has. And what quantum mechanics predicts is that we can take the wave function describing some system, potentially even something macroscopic like Captain Kirk or you and me, and we can take that and destroy it in one place and reproduce it in another place and make that wave function out there, wiggling again. So there'll be a Captain Kirk which in every possible way that we know how to test will be like the original. Now, is that the same Captain Kirk, or is it a different one? Does he have the same soul? Is there even a soul there? Maybe these will become experimental questions if we get to the point of being able to teleport very large-scale systems.
How does this work? Even if we're doing it on levels of photons or simpler quantum objects, how do we teleport things in this way?
Well, if we just tried a simple way, which is just to measure the system and try and read out what state the system was in, then in a sense the Heisenberg uncertainty principle would disallow you. You could measure, say, something about the position, but the velocity information would be destroyed, or vice versa. So you'd never gain full information. The surprising thing about quantum teleportation is that you add one extra ingredient, which is that you share between the sender and the receiver a weird quantum mechanical state, some correlated pair of particles which are entangled. So you share entanglement between the sender and the receiver, and with that shared resource, it turns out that now, when you make a joint measurement on one half of the entanglement and the system that you want to teleport, the information you get is a mix of the two. So you don't learn directly about the position, you don't learn directly about the velocity or anything like that. In a sense, what you do is you learn something about the correlations or the overlaps between the one half of the entangled state and the state you want to teleport. And learning about those correlations, in a sense, you've built in correlations from the system you're trying to teleport to the distant end, to the other half of the entanglement. And now if the person who has the other half of the entanglement in the receiving end is told what correlations were built into the entanglement through this measurement by the sender, he can essentially do some operations which I guess I like to think about as being like a Rubik's Cube operation, somehow unscrambling what would otherwise look like two halves of some random state, although they're really entangled. And then what comes out of this is the original state. It's really pretty remarkable.
That means if you're sending your scrambled information across classically, say by radio or by telephone wire, and you're storing it classically at the other end, and then you're interacting it with the entangled states, does that mean that you could, after you've reproduced your original, you could take your classical pattern out of the computer again and again interact with an entangled state to get a second copy?
Well, no, and the reason is that you're only using one copy of shared entanglement to do the teleportation. And so the randomness that you get is intrinsic to that particular entangled pair. And if you tried taking a second half of some other entangled pair, its correlated randomness would be completely different, completely uncorrelated, so to speak. And so you would just get gibberish out. You would just get some mangled mess instead of Captain Kirk, so to speak. And so the weird thing is that although you're converting this quantum mechanical system, which is very fragile and which you can't copy because the uncertainty principle doesn't let you, nowadays we call that the no cloning theorem,
cloning in a totally different sense to the genetic sense.
Well, yes, and not in the genetic sense, but in the sense of producing duplicates. So, although we can't convert a quantum system solely into classical information, teleportation allows us to convert it into classical information plus a shared resource of entanglement. And so by sender and receiver sharing this special resource, he can now use the classical information and then reproduce or reinvigorate whatever the original system.
But you'd only be travelling at, say, light speed or slower.
Yeah, the fastest this quantum teleportation allows you to travel is the speed of the classical communication transfer, which you require to be able to tell the receiver, or the person who's going to be reproducing Captain Kirk, so to speak. He has to be sent classical information talking about the correlations that were built in by the sender.
So if something goes wrong and the entanglement system doesn't quite work, then the original state is destroyed.
Unfortunately, it has to be, because if the original state was not destroyed, then if you completed the teleportation protocol, end up with a duplicate, but then the original would still be there, and that would violate this no cloning theorem. This would violate essentially the Heisenberg principle.
So what are the applications in the near future? I mean, obviously, Star Trek style teleportation is a long, long way away. What's the applications in the very near future for quantum cloning and teleportation?
Well, let's see. Just to give a fun idea of timescale, if we were very optimistic about how our ability to process information was going to be growing, we know already that in conventional computers, classical computers, their power improves doubles about every 18 months. Now let's suppose that ability to process information kept increasing at that rate, doubling every 18 months, not just for the next, say, 15 years, which people in the computer industry believe will be the case, but kept going for another 100 years. That's about the timescale we would need to be able to be processing as much information in a human body to be able to, well, more or less to be able to teleport a person. That's being very, very optimistic. It's probably going to be much longer. In terms of present-day applications, quantum teleportation is really quite an amazing protocol, I guess is the way of describing it. It's some fundamental way of being able to process quantum information. And what you can do is you can robustly transport the quantum information because you're sending it along a classical communication channel. Classical communication channel could be almost anything. It could be light along an optical fiber. It could be electrical signals down a wire. It could be someone laboriously writing out letters and then putting them in an envelope. You could fax the information.
So you could be faxing the person.
You could be, in a sense, faxing the classical information. That could be part of your entire quantum teleportation protocol, but you'd still need to have shared entanglement to complete it.
You're listening to Diffusion Science Radio. Diffusion at 2SCR.com, brought to you across Australia on the Community Radio Network.
Dr. Braunstein, how do you transport the entangled systems that let you reproduce the original?
Well, unfortunately, that has to be a little bit on the laborious side, just as if we had a quantum mechanical state in some beaker or something like that, or some special refrigerator, keeping it cold and isolated from the outside world, we might take the refrigerator, holding it, and actually physically move it from one place to another. Now, that's kind of tedious to do. However, the nice thing about transporting something with quantum teleportation, rather than physically taking it and moving it inside a refrigerator, is that if instead we just distributed the entanglement, we could distribute the entanglement, so to speak, off-peak. So at nighttime, when people are not using the roads and it's safer, so that no one's going to crash into our car holding the refrigerator, we can send large amounts of entanglement at off-peak prices. And then when we want to teleport something, some fragile quantum state, we can do it, on demand, and we can do it at the speed of light, the speed limiting our classical communication. So, for instance, if we wanted to be able to teleport a person, what we could do is build up a large number of entangled pairs sufficient to be able to describe the complexity of a person, and then when a person, say, needs to be able to move from Paris to London, what he can do is he can move and get into the teleporter, get discombobulated, so to speak. He's destroyed, and then the classical information describing his correlations with the half of the entanglement in where he is, then get transported at the speed of light, and he can be recombobulated, so to speak. So the traveler can move very quickly, but the entanglement has to be shared rather more slowly because it's physical massive particle.
But once it's there, it can be used at the speed of light.
That's right. So there are some real advantages by being able to leverage the way we manipulate quantum systems in this way using quantum teleportation. Other things that we can do, because quantum teleportation allows for the very robust motion of what would otherwise be very fragile systems, there might be other advantages, like there's a thing called quantum cryptography, where one hopes to be able to perform a cryptographic protocol, so send a secret code in a way that even if an eavesdropper is trying to listen in and trying to catch the secret key that you ultimately have to share between the sender and the receiver, that you can find whether the receiver's there, and that's based on the fragility of quantum information. An eavesdropper who tries to look at it invariably will leave his footprint.
And once again, it depends on shared entangled states.
Yeah, not all quantum cryptographic protocols require entanglement, although, and it's still not completely clear which is the best kind of protocol. Recently there have been, it's an ongoing question. Quantum cryptography really only requires the fragility of the quantum states to work, and that can be done either in a way which uses quantum entanglement or in just using straightforward quantum states.
Can I just get the point clear? A quantum entangled systems from the same source. So you'd have one source, and basically you've got two physical objects or two physical sources in the recepting place, the place that you're teleporting to, the place you're teleporting from, and these are sort of quantumly connected, and that's why you're able to do the teleportation.
Yes. In fact, we don't really have a good classical way of being able to describe what entanglement is, and so some of the very top people in the field resort to metaphorical descriptions. So in particular, there's one by Charlie Bennett. In fact, he has a couple, but maybe I'll start with one. An entangled pair of particles are, in some sense, a little bit like two lovers. Even if they're well separated from each other on the opposite ends of the world, or, on one side of the universe and the other, you could think of asking one of the lovers a question and ask them what would their lover answer. So the two lovers say Alice and Bob, and you can ask Bob, what would Alice answer to such and such a question, which neither of them had ever heard of before. And nonetheless, because of their somehow strong correlation, the strong feeling, the strong love between them, Bob is able to say what Alice would answer, even to a question which he'd never come across before. And so entanglement's a little bit like that. The two systems are somehow strongly correlated, more strongly correlated than any classical description could make sense of. Actually, there are other ways in which that metaphorical description work. Alice can be entangled with Bob, and if she is, she can't be entangled with someone else, Charlie. But suppose she became entangled with Charlie, so she fell in love with him, then she would have to fall out of love with Bob, and similarly, she becomes entangled with Charlie, she would have to become unentangled with Bob. So in a sense, entanglement, like love, is monogamous.
That was Dr. Samuel Braunstein talking about faxing yourself from one side of the universe to the other. Next up, here's Pie Man. You're listening to Diffusion Science Radio, but have you ever wondered how your radio works? Here's Patrick Rubie with the history and science of radio.
Radio waves are just one part of the electromagnetic spectrum. All light, sound, and radiation exists as a variety of waves, with corresponding magnetic fields called the electromagnetic spectrum. So the light that allows us to see, the sound waves that allow us to hear, and the X-rays that allow us to see through solid objects are all part of the same spectrum. In the mid-1800s, Scottish physicist James Clerk Maxwell demonstrated the connection between waves and magnetic fields and developed a theory for this connection based on the work of previous scientists including Michael Faraday. But it was the German physicist Heinrich Hertz in 1886 who discovered radio waves specifically. He demonstrated that rapid fluctuations in electrical current could be transmitted into space as radio waves. When an electrical current is set up, you can use a voltmeter to measure the voltage of the circuit. If you place another voltmeter in an unconnected circuit close by, you might be able to pick up a weak voltage signal from the first circuit. This is because the moving electrons in the first circuit give off a magnetic field, which is picked up by the neighbouring circuit and transmitted to that second voltmeter. This is the principle of transmission. One of the most famous names associated with radio is Guglielmo Marconi. In 1895, Marconi sent the first wireless telegraphy signal in Italy, and in 1901 he received the first wireless signal transmitted across the Atlantic from England to Newfoundland. It was the letter S. He had filed many patents on wireless technology in the late 1890s, sparking feuds of intellectual property with other inventors such as Nikola Tesla. Nikola Tesla is credited as being the first person to patent wireless technology. He conducted many experiments in radio transmission in the 1890s, had his patency of the wireless withdrawn by the US government in favour of Marconi around the turn of the 20th century, and then had it reinstated posthumously in 1943. Since then, there have been numerous other scientists and physicists that have advanced our knowledge of the use of wireless or radio. Radio began to be used by naval ships for communication by the time of the First World War. By the 1920s, public broadcasting had begun, and people could listen to broadcasts on wireless sets. And now for the science of radio. Radio waves are at the big end of the electromagnetic spectrum. Their wavelengths range from about half a centimetre to about 50 kilometres long. Their frequencies range from 10,000 Hz, or 10,000 wave cycles per second, for the biggest waves, to 100 billion Hz for the smallest waves, which if you think about it makes a lot of sense, because these waves all travel at the same speed, so the little guys have to cycle more frequently to keep up with the big guys. Radio waves are not just about radios. They are harnessed in cordless and mobile phones, TVs, remote-controlled toys, and even baby minders. So how do we put specific sounds onto these radio waves? How are they transmitted to our audio devices? And how do these devices deliver them to our ears? These three questions form the basis of radio.
Transmitting diffusion science radio. From Community Radio Network to your brain. And that's all from us in this edition of Diffusion. Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com. Contributing to the program were Patrick Rubie and Ian Woolf. I produce Diffusion, which is broadcast around Australia to 27 stations on the Community Radio Network, including 2RBM in the Blue Mountains of New South Wales, 8CCC in Alice Springs and Tennant Creek, 2NVR in Nambucca Valley, 3MBR in the Mallee Border districts of Victoria and South Australia, and 7LTN City Park Radio in Launceston, Tasmania. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.